Hello everyone. So now let's look at the crystallographic planes for the hexagonal close-packed structure. Now for a hexagonal unit cell, we can use a similar procedure. However, we have what it's kind of like four different axes. We have three on the bottom, which are going along, each of these directions for the bottom, and we have the z-axis still. So we have to choose where our origin is going to be and see, is our plane intersecting that origin? In this case, no it's not, so we don't need to do it. Where does it intercept? Well, we're only doing it in terms of A1, A2, and the z-axis. For the A1 axis, it intersects at a distance A. Okay. For the A2 axis, it never intersects. And for the z-axis, it intersects a distance c, because it's one height. And the height is considered to be c. I take the reciprocal, so the middle one goes to 0. And then I normalize. So I have a distance of 1, 0, 1. So it's always in terms of HKL for the hexagonal close packed. But you might be wondering, well, what about this I right here? What about that I? Well, to determine I, it's simply equal to negative h plus k. There is a fourth index for a hexagonal close packed structure. So it would become negative 1. So your Miller-Bravais indices would be HKIL, that's what it is right here, HKIL. And you plug in all the numbers, and you get 1, 0, negative 1, 1, and we make it a 1 bar, just because of convention. I will not ask you to do this much, if at all, in this class, but I still want to show this to you just so you get a little bit of experience seeing these planes in a hexagonal close packed structure. Okay, now we've gone through all the structures, let's talk about the planar density of atoms. You're like, oh wait, yeah, we did linear density, now we're going to do the planar density of atoms. So we need the number of atoms that's centered on a particular plane, as well as the area of that plane. So let's look at the planar density of the 1, 0, 0 plane of body-centered cubic iron. If you're wondering what the 1, 0, 0 plane is, I'm not sure I can draw this as nicely as I'd like to. Okay, we got this one right here, we got this one right here. Yes, and here. Beautiful. Then we have that guy in the center. So the 1, 0, 0 plane is this plane right here. It does not intersect the central atom. That's why you see this big gap in the center. It just has those 4 atoms at the corner, but there's slight spacing. Now, from our work with finding the atomic packing factor of the body-centered cubic cell, we know what A is in terms of R. It's 4 over square root of 3R. If we're looking at this plane, we need to find the unit that actually repeats. It's not 100% important that you do that, that's just the simplest way to find it. Now, in this case, there are 4 quarter atoms, and it says 1 atom centered on this plane. If you're wondering, well, like last time you said it's a radius, that was because it was a line. This time, since I'm doing a 2-dimensional space, I have to look at the areas. The area that's actually being cut here. It's always going to be like quarters or halves or wholes for this. You might see a third or something else like that. That would be very rare. And so, see, I'm looking at an atom as a whole circle in this case. And so, since I have 4 quarters of a circle, it turns into 1 atom. So, linear density, think of how many diameters do you have? For planar density, how many circles? So now if I know this, I can then plug in my numbers. I know what the radius of iron is, 0.1241. I can get what the size A is. From that I can get the area. And so what I get is 1 atom per 0.287 nanometers squared, or 12.1 atoms per nanometer squared. and that is the planar density. Now, why do you need to know this? Well, the more atoms in a particular plane, the more closely packed they are, and various mechanical properties will depend on that. So, it might not seem like this is important, but these are the skills you're going to need to understand why things happen later on. So, thanks for listening. I think that's everything. Yes, it is. And I'll see you all next time.